All right, next speaker is Dr. Nathaniel Putzig from the Planetary Science Institute. Welcome to the conference. Your topic today is exploring for underground ice on Mars.
Great, thanks much, James. All right, great. So I'm at the Planetary Science Institute at our office in Colorado. I am a senior scientist here with PSI. I also serve as the US team lead for the SHARAD shallow radar instrument on the Mars Reconnaissance Orbiter. And I'm one of two leads on the so-called Mars swim team. Today I'm going to focus in on the results coming out from the efforts by the Subsurface water ice mapping Mars swim team. Before I get into it, I want to make it clear that this work is supported by many other people. I want to thank the MRO project, the SHARAD team, my co-captain on swim, Gareth Morgan, and the rest of the team for all of the efforts that have gone into this work. So I thought I'd start by reviewing some of the past work from a set of different orbiters at Mars, detailing what we know about buried ice on the planet. In general, multiple data sets from different spacecraft point to the presence of buried ice outside of the polar regions. For example, this map here shows global water equivalent hydrogen within the upper meter, because the neutron spectrometer that detects the hydrogen can only sense the presence of that hydrogen within the upper meter or so. The dark blue areas are where there are very high concentrations of this water equivalent hydrogen. And these are inferred to contain so much hydrogen that the only reasonable explanation is water ice. In the mid latitudes and down at the equator, you see these fainter blue areas. Many of these have been inferred to be representative of the presence of hydrogen in the form of hydrated minerals, so not necessarily any water ice involved. Another means of detecting water ice is to essentially take the temperature of the surface over a series of times of day or seasons, and then compare that against thermal modeling work to ascertain whether there may be a layer of ice in the shallow subsurface. And using this technique, one finds a pretty close correspondence to where the neutron spectrometer is detecting all that hydrogen. So this is a thermal measure of the presence of buried ice. It can extend mostly down to about a meter, and in some instances, maybe up to a couple meters depth. So this shows that ice appears to be widespread in the high latitudes of Mars, both in the northern and the southern hemispheres, down to about 50 degrees latitude. So we have a host of other information about buried ice. For example, all of the orbiters carry some sort of camera in general. The cameras often show us landforms, like shown in the image on the left here, that have all these flow features in them. And these have long been thought to contain some amount of ice. And in fact, in other areas, we find new impacts that we've detected by multiple imagings of the surface, where suddenly these bright patches appear. And both from the visible data and from spectrometer data, we know that this bright material is water ice that appears at the surface shortly after the impact occurs, and then it slowly sublimates over months or years as determined in follow-up imaging. So another method that we use to infer the presence of ice is radar sounding. So radar soundings have been quite successful in detecting the base of both debris-covered glaciers and ground ices on Mars. And these are measured down around several tens to several hundreds of meters depth. Again, these are basal detections, or they're thought to be basal detections of ice. The radar gets a really strong return off the base. And this is a pretty clear indicator that that ice has to be relatively pure. There can't be a lot of admixture of soils within the ice to attenuate the radar signal. So the image on the left here shows a ground track of the Mars Reconnaissance Orbiter path over a Mars Orbiter laser altimeter shaded relief map, where you can see some of these geomorphic features associated with these mesas that are these debris-covered glaciers. And then the radar gives us a profile view where the basal detections are pointed out here with the white arrows. And when they're depth corrected, assuming a pure water ice content, they are much contiguous with the surrounding terrains, giving us a high level of confidence that this really is a fairly pure deposit of ice. However, the radar doesn't really resolve the upper surface of these ices, so we don't know from the radar exactly how thick the debris cover might be. Similar radar soundings over areas beyond the glacial landforms, kind of out in the plains of the northern hemisphere. Occasionally we'll find these fainter reflections, and we're able to determine the depth to these radar reflections by correlating them with features like these impact craters that have, in this case, terraces associated with them. And we can infer a connection between this radar detection and that deeper terrace in this crater. And doing the math, we figure out that there's an awful lot of ice in the material overlying that interface. So I mentioned the swim team. Now, so many of the studies up until fairly recently have focused in on one of these data sets or a small region with multiple data sets, but there hasn't really been a kind of a holistic examination of all this data to see and map out what is telling us about the presence of ground ice. That was kind of the impetus behind the formation of the SWIM project and the assembly of the team. It really came out of a workshop that NASA had in 2015 to start looking at human landing site areas. And collectively, the group realized that, the presence of water ice would be really critical to serve as a resource to sustain a human presence. So with SWIM, we're trying to integrate all of these different data sets with their different sensing depths to get a broad view of what we know now with these data sets about the presence of that ice. It's a big team. There's a list of everyone on it. I won't go through it, but there's quite a few institutions involved around the country and around the world. It's been funded by NASA through a contract with JPL for on and off for the last several years. So the data sets in particular that we're using come from 3 different orbiters: Mars Odyssey, the Mars Global Surveyor, and the Mars Reconnaissance Orbiter. We use neutron data from the neutron spectrometer, thermal data from 3 different spectral instruments, TESS, THEMIS, and MCS, and they're on each of these spacecraft. Geomorphic information mostly from imagery on the Mars Reconnaissance Orbiter, CTX, and HiRISE instruments. And then that radar data set that I introduced, we use 2 aspects of that actually, those subsurface discrete boundary detections, and then a shallower detection in the very upper near surface, kind of an integrated detection of potential presence of ice from the so-called surface return of the radar. That senses down to about 5 meters depth or so. So these kind of discrete data sets tell us information about the upper meter and below tens of meters, and we can kind of infer down to about 5 meters with Schrödinger surface return, but there's no like really clear way to detect interfaces in between, say 1 meter and 15 to 20 meters. Geomorphology and this radar surface return are helping us bridge that gap, but eventually I think we're going to want to get better, well, instrumentation that's tuned to try to find the ice in this zone. And I'll get into that more in a little bit. So with each of these data sets, we isolate a particular property or properties of the subsurface for a given depth range. And then we assign it a value of what we call ice consistency. So this is the consistency of that data set with the presence of ice in its sensing depth. We call this C, and that value of C consistency ranges from -1, meaning the data says there cannot be ice here, to 0, where the data is sort of agnostic as to the presence of ice, all the way up to +1, where the data set is essentially screaming, this has to be ice in the ground. So I'll just take you through a few of these data sets and the mappings of them. So this is from the thermal data. We use the thermal data from TESS and other instruments to establish a depth to potential ice. We averaged together the results that we did on the swim team together with that of prior workers, using the thermal method like I showed earlier, to come up with a consistency value for ice in this zone of about 30 to 50 centimeters depth. And this is how it maps out across the planet between plus and minus 60 degrees using our techniques. So the deeper shades of blue indicate greater consistency with the presence of ice. The whiter end here is going towards that agnostic 0 value where we're not really sure if the data set is telling us much about ice. Then for that radar surface layer, or surface return, as I mentioned, that gives us a sense of the potential presence of ice down to about 1 meter. This is because ice is a lower density than your typical materials that make up the Martian soil. And that lower density leads to a lower power return from the radar. So then this is a map of how the radar surface returns translate to these consistency values across the surface of Mars. So I mentioned geomorphic mapping. So for SWIM, we do mapping of a total of 8 different landforms in what we call a grid mapping sense, where you look for the landform in a area of a given size. We use different grid sizes for different aspects of the study. Some are as big as 10 by 10 degrees, some are as small as 1 by 1 degree. And we essentially count up the number of ice-related landforms within each grid cell to determine the consistency of ice. So that's how that measure maps out across the planet. I delineated two portions of our study from 2019 and 2020. In 2019, we had less time to actually work on the geomorphic mapping. And so it's a much coarser mapping. Most of the grid cells are 10 or maybe 4 degrees across. Whereas in the 2020 phase of the study, we were able to do a lot of this 1 by 1 degree mapping down near the edge of where this ice sort of peters out at the lower latitudes. So we're going to continue this work. I'll mention a little more about that toward the end. Finally, the radar subsurface returns those discrete reflections off the base of the ices. We use those to estimate from the speed of the radar wave through the materials. We can estimate the material properties and whether or not those are consistent with ground ice versus just regular soil or bedrock. If they have a lower value of this parameter dielectric constant, then that's more consistent with ice. So that's the bluer areas on the map. These tend to be much finer scale. They don't really show up all that well at this scale. If we zoom into area around Hellas, we can see more of these scattered detections from the radar of the base of these glaciers around the edge of these mesas in the eastern Hellas region. So how do we kind of amalgamate all these data sets together? Essentially, we take several different approaches to tease out different aspects of the data. If we I'm sorry, let me back up here a slide. If we take each of the consistency measures from all of the different methods and just simply average them together, we get this view here. So this is sort of a holistic view of where the ice might be. It doesn't tell you much about how deep it might be, but it gives you an idea of what our level of confidence is across the suite of instruments. And so, it tends to be more confident at the higher latitudes, but it does extend down in well below that 50-degree line from earlier work. It also lines up quite well with where these ice exposing impacts have been identified across the northern plains and a few down here in the southern hemisphere as well. However, because there are different, each instrument type or method looks at a different depth, one can tease out different depth zones, maps of different depth zones. So here's a map for the depth zone from 0 to 1 meters. And here we then take the different consistency values from the different techniques and weight them differently depending on what their sensing depth is. So that 0 to 1 meter range is really dominated by the neutron spectrometer and the thermal spectrometer measures, but the radar surface return and the geomorphic mapping also has some influence. So those included in this equation for ice consistency in this zone. Again, because of the shallow sensing depth here, things are sort of more concentrated in the highest latitudes where we know there is very shallow ice. If we go down another zone down to 1 to 5 meters depth, then we use a different equation that drops out the very shallow methods of the neutron spectrometer and the thermal spectrometer and focuses in on the radar and the geomorphology. And this extends down to the lower latitudes, but there isn't quite as much variation with latitude, predominantly due to the fact that we have that sort of blind zone from 1 to 20 meters, And these data sets are only giving us some indication of ice in those zones without really delineating it as a function of depth. Finally, if we go to a deeper zone, we really then are concentrating just on the geomorphic features that are consistent with very deep ice and the radar detections of the base of those ices. So that gives us this view here. Another way, I started with a holistic view of averaging everything together. Another way to look at that is to then just take those 3 depth zone maps and average those together. And that gives you a somewhat more subtle view of where the ice might be and our confidence in the presence of the ice in different geographic regions. So that's this view here using the depth zone averaging method. And one can go on and kind of slice and dice these data sets in different ways. So I'm only going to show this one more example. Here it's essentially an overlay technique where we overlay the different depth zone maps to provide yet another holistic view. In this case, we set a per zone threshold on that ice consistency value. So we're only including the higher significances. That is, ones where more than one data set is showing us strong evidence for that ice. This, by and large, breaks out into 2 zones here, the blue and the purple zones for the shallowest ice and the intermediate depth ice. But the green zones then are where that deep sensing radar data is really screaming. There's a lot of high purity water ice here. The geomorphic features kind of drop out in the thresholding of that deepest zone in this method. Now, if you don't like the way that we're putting these different methods together, feel free to make your own maps. These data and the maps that go into them are all available on the SWIM website. These are full GIS-ready products from the 2 phases of mapping. They're browse images to help you orient yourself with where the data are from. Descriptions of this work are in a paper in Nature Astronomy that came out earlier this year by Morgan et al. And there's a book chapter in the book I'm sure all of you will want to rush out and buy as soon as it's on the shelves, called The Handbook of Space Resources, which will tell you everything you need to know about finding resources in space. Just as a final note, I want to talk a little bit about what's next. Many of you are probably aware that a number of different space agencies are working towards putting together an international Mars ice mapper mission. Essentially, one of the main goals of this mission is to close that gap in sensing depth that I mentioned, to really zero in on exactly where these ices are, how thick is the overburden, what's the nature and concentration of the ice, what are the material properties of the overburden. In addition, the SWIM team is regrouping for another season. We're going to refine the geomorphic mapping more and also more explicitly try to work together with the IMEM team to better inform the planning for that mission. Meanwhile, the Mars Reconnaissance Orbiter and other spacecraft continue to target these ice-rich terrains to try to better characterize the extent and properties of the ice with the tools that we have now in orbit. And I want to direct you to another talk in this convention called Engineering for Mars on Friday. This is by the British Planetary Society members Fabrizio Bernardini and Rennie. They're going to discuss the impact of these buried ices on the engineering considerations for extracting the ice and doing exploration once you're on the ground. So with that, I'll close off, and hopefully I left a little bit of time for some questions.
Yeah, we've got 4 minutes left here, Than. Let's first, I bet you've never gotten a question from VR before, so let's see if we could try that out here. Jay, do you have a question? Let's see if I can get you guys on board here. You could start video, Jay.
What instruments would you like to see land on the next mission?
You say land, so I take it you mean, so I mentioned the Mars Ice Mapper, so I think that's a great idea for another orbital mission to kind of zero in on things. But yeah, when you get to the ground, then you really want to pinpoint exactly where the ice is and figure out where you're going to start drilling or excavating to get to it. And so I think to help with that, I'd really like to see a combination of ground penetrating radar to help tie in with the orbital radar, in addition to other methods such as active source seismic tools to use acoustic waves to explore the subsurface, and then electromagnetic methods, as well as gravimetry, I think would be very helpful in trying to delineate on the ground at the landing scale exactly where the ice is and what its properties are before you start actually now drilling down to make samples and evaluate them in a laboratory setting.
Thank you.
Than, can you repeat the name of the book you mentioned?
It's the Handbook of Space Resources. The publisher is Springer, and it's getting close. I think most of the chapters are finalized. Ours is ready to go. We have a chapter describing the swim results. So yeah, stay tuned. I think that'll probably be out in the next several months.
Okay, great. Lyra, do we have any questions in the Q&A panel?
Yes, we've got a lot of questions, and it definitely would be great if Mr. Putzig, you can after follow up with the people via text, but I'll read one of the questions. So the question is, it says, what is the current working range for a source of water ice to an early settlement? I guess it's for an early settlement.
Okay. Yeah, I mean, that's going to depend a lot on the engineered ground systems. So I guess I would refer you to that talk on engineering that's coming up tomorrow. But offhand, I'd say, ideally, at least on a first mission, you'd want to land where there's ice in the subsurface, or very close to it, within a kilometer or less. And I think that's feasible. A number of these debris-covered glaciers occur in areas where there is also likely ground ice. And the debris-covered glaciers might be a little rough for landing, especially first landing, where you can't really improve the landing surface before you come in. So I think landing near one of these debris-covered glaciers where there's also distinct possibility of ground ice in the vicinity or right below the landing might be an ideal situation. And I think with the swim work and more focused efforts, I think we can kind of zero in on such landing sites in the next several years leading up to future landed missions.
Okay, great. Thank you so much, Dr. Putzig, and thank you for participating in our event today.
Thanks for the invitation.